you. Sorry about that. So good morning, everyone, and thanks for the opportunity to talk a little bit about the blowing snow model. Certainly, this is a collaborative effort with several folks in the Northern Plains, led by Tommy Grafenauer in Grand Forks and Steve Flegel in Aberdeen, and I get the pleasure of visiting a little bit about it, but certainly I want to emphasize that this is a collaborative effort. To start with, I kind of want to make the case that certainly blowing snow is a problem across a large part of the CONUS, not just in the Northern Plains. Coleman and Schwartz did a climatology annual probability of blizzards back in 2016 across the lower 48. Certainly we see that the numbers are pegged out across the Dakotas, where we frequently see blizzards on average close to once a year, but certainly really no part of Central Region totally immune to blizzard potential. So when we're talking about blowing snow, the work we're doing certainly is applicable to a wider area. We know that the blowing snow and blizzards certainly a significant impact, but how do we forecast it? And that's really the question that we're getting at with this work, is how do we forecast it, and how do we forecast it scientifically and consistently? On the right-hand side, there is an example of a pretty typical forecast problem that a lot of you see, and we certainly see it in the Northern Plains as well. We're trying to differentiate between the winter storm conditions, where perhaps there's heavy snow, but not lowered visibilities due to blowing snow, from the blizzard conditions, which of course the red there is the blizzard warning from parts of central North Dakota down into northeast South Dakota in that particular example, and then high wind warning on the backside, where perhaps we don't have pre-existing snow on the ground, since we already have that ground blizzard problem in the Northern Plains, as well as a lot of other parts of the high plains, of course. So where do we really draw the line consistently, where we can sort of outline not only the hazards, the watches, the warnings, but also the messaging directly related to IDSS? So a lot of what we'll talk about here, a lot of the work that's being done is directly applicable to things that are being in GFE, but really it applies to all of the IDSS. So in the past, a lot of you know that we had real inconsistent philosophies. If you go back the last 10 or even 20 years in when we would put blowing snow in the forecast, when we would decide to issue blizzard warnings, especially for our ground blizzard problem. We even had differing definitions and messaging strategies, of course, for blowing snow regionally and really across the CONUS. So there was a realization that we needed a science-driven solution that had service-oriented results. And the desired outcomes that we had going into this work, and as the work has gone along, which I think we've achieved, are certainly more consistency in our messaging approach and our warning decision, WAWA decisions, using a peer-reviewed approach. So again, it's that science-driven solution. And then as we've kind of come full circle, and the last couple of years, we've actually added the use of a definite quarter mile blowing snow NDFD category, because in the past we would emphasize blowing snow in the grids. We knew there were blizzard conditions, but really the point and click would just say blowing snow. When reality is we have that option to add a little bit more amplitude to the messaging, even through the legacy, if you want to call it that, sort of point and click messaging. And then also we've started to use patchy blowing snow for drifting snow impacts, and I'll make a case for why we're doing that going forward, since we don't really have drifting snow currently as an NDFD weather grid category. So several factors influence blowing snow potential, but it turns out that operationally they can really be tied together empirically. Of course, we know that wind is an issue when it comes to blowing snow, and probably one of the biggest driving factors when it comes to blowing snow, as well as snow rate. But Baggaley did some work back in 2005, and he developed an empirical model based on a lot of Canadian data that gives probabilities of visibility thresholds being reached due to blowing snow. So his work suggested that also temperature is vitally important, partially due to crystal structure and things like that of the snow, both falling and on the ground. Of course, again, wind and snow rate are important, and the snow age, which relates to the snow that's already on the ground, our pre-existing snowpacks, and we're starting to talk about ground blizzards, or the contribution of snow already on the ground to those sort of blizzard conditions. Turns out from their empirical model, snow age is particularly important in that you need fresh snow with having fallen largely within the last 24 hours or so to really have amplitude of those blizzard conditions. But their empirical model gives us probabilities of different visibility thresholds being reached, including the visibility or probability rather, of a half-mile visibility. So the Baggaley model, Jeff Makowski, who's now in La Crosse, and then Tommy Grafenauer in Grand Forks, they published a Central Region technical attachment a few years ago that compared the probability of a half-mile visibility from the Baggaley empirical model to impacts using blizzards that were observed in observations from the Grand Forks CWA over the span of about 8 or 10 different winter seasons. And it turns out that there's a direct correlation between increasing probabilities of a half-mile visibility from the Baggaley model and impacts. And it turns out that once you start to get up to probabilities from the Baggaley model of a half-mile visibility of 60% or so, and when you really start to see sort of these isolated to what they had described as isolated to scattered blizzard conditions. So in other words, it might be okay in town, but periodically bad in rural areas. That's when you're starting to get to the fringe of advisory type conditions, perhaps. And then as the probabilities went up, certainly once you got the probability of 80 or 90% of a half-mile probability from Baggaley, the impacts became really high or very high to where we were getting pretty widespread blizzard conditions, and really getting widespread blizzard conditions both in rural areas, which is common, of course, in the plains, and in town where things are more sheltered. Usually in those cases, we probably have heavy falling snow, which is also, again, taken into account by the Baggaley model since it accounts for snow rate as part of its components. So the Baggaley model is particularly sensitive, again, not only to wind speed, but really also to temperature and the snow rate. So this particular graph just pulls sort of some of the empirical nature of the Baggaley model as an example for the probability of a half-mile visibility, just using a half-inch per hour snowfall rate for 3 different scenarios. One scenario is having temperatures of 30 degrees Fahrenheit, one is at 20, and one is at minus 20 Fahrenheit. And what we see is to get an 80% probability of a half-mile visibility with a half-inch an hour snowfall rate, at 30 degrees, you need a 35 knots largely sustained wind at that probability or at that level. However, as you go down colder temperatures, it takes less wind. And so by the time you get down to minus 20, with a half-inch an hour snowfall rate, really, and you get into those Arctic air masses, the Baggaley empirical model would suggest that you actually only need sustained winds right around 22 knots or so to produce that 80% probability of a half-mile visibility. We know from the Makowski and Grafenauer work that that correlates pretty strongly to blizzard conditions. You can actually kind of get into the nature of the empirical model. It turns out that at certain times, a 1 to 3 knot increase in the wind speeds is sometimes all that you need to reduce the visibility from like a half mile to a quarter mile. So that's some of the other effort that came out of the work that Jeff and Tommy did previously. So the Baggaley empirical model is developed for blowing snow, but we know it doesn't capture drifting snow impacts. And we certainly care about drifting snow because there are impacts from it. One of the things that we deal with a lot during the winter time in our part of the world, and certainly in parts of yours as well, is where we will get what the road weather folks refer to sometimes as blow ice. In other words, we have a sunny day with moderate wind speeds, pre-existing snowfall on the ground that drifts across roadway surfaces that warm above freezing in the sunlight, even though the air temperature might be below freezing. The snow then melts and refreezes on the roads, especially later in the day, and you can get really, really slippery black ice conditions, even despite sunshine. The example there is from the North Dakota Highway Patrol, a tweet from a year or two ago where they had numerous accidents from what this sort of blow ice thing. So we want to sort of capture this low drifting snow. It's still observed by the public and obviously can have dramatic impacts. Work that was done at the NWS La Crosse office, Dan Baumgart and Andy Just, I believe, both involved at this. It turns out that 17 knots is about where you start to get drifting snow to occur. And then the graph there is from some other peer-reviewed research, sort of lines up pretty well. 17 knots is a pretty good threshold where you start to get this drifting snow that's observed by the public and which can have impacts. So the blowing snow model that we actually have in Forecast Builder then ties all of these things together. We were able to match them to the NWS grid definition requirements that provides us our IDSS consistency. And so patchy blowing snow in Forecast Builder and in this methodology is either where we have wind greater than 17 knots or greater than or equal to 17 knots, which again gives us our sort of pseudo drifting snow application, or if we get a 10% probability of visibility less than 3 miles from the Baggaley model. We really focus on the half-mile visibility threshold from the Baggaley model for our blizzard IDSS and messaging, but there are other visibility thresholds out of Baggaley, one of which is 3 miles. So we then assign areas of blowing snow with a 30% probability of the visibility being less than a mile per the Baggaley model. And then we get up to those definite and those blizzard categories where, again, the definite blowing snow that we see in Forecast Builder is where we have a 60% probability of the visibility being less than a half mile in the Baggaley model. And then blizzard, accordingly, 80% greater probability of the half mile less than that for the Baggaley model. So we know this is in Forecast Builder. One of the recent efforts that we have done in the Northern Plains between Aberdeen, Grand Forks, and our office over the last year or so is to actually develop another independent procedure that you can actually use to run the pot blowing snow, but it's not so much to directly create pot blowing snow grids, which we do through Forecast Builder primarily, but to give some of these other sort of sensitivity testing type of things, which I'll show here on a coming slide. But on the right there, of course, is the example blowing snow model grid. Many of you are probably already familiar with that if you're from an area that deals with blowing snow at all. And again, converting those Baggaley thresholds and other things over to our IDSS sort of grid definitions. And again, the standalone tool, which we will eventually be able to share with everyone in the sort of final stages of development, will actually let you see sort of the raw background probabilities and things that are going on with the Baggaley model. So in order to account for ground blizzards, we needed to know where the pre-existing snowpack was. We're doing this through NOHRSC, and if you've run Forecast Builder, you've probably got this banner that says, hey, you can set the snow depth to 1+ inches where global snowpack exists and 0 where it doesn't. Well, you get a first guess from that based on the NOHRSC data from the last 7 days and the last 7 days worth of temperatures greater than 35 to determine, say, when the snowpack that's on the ground may have sort of crusted over and no longer being able to be blown. You see the example image there, or loop rather, sort of shows how that snowpack in the background is created. Again, we had snowpack on the ground, temperatures melted out, so you see the blowable snowpack go to 0, and then at the end of the loop, you see actually 1 inch of new fresh snow falls in the southwest part of North Dakota in this example, because the methodology going forward in Forecast Builder will account for any forecast snow that you have in your grids. So the GFE output can then be used to develop messaging both indirectly and directly using graphics packages. Here's an example from Aberdeen from last year where the pot blowing snow grid is on the left. They've then converted that over to a blowing snow threat graphic that's sort of a 3-colored system, and then tied it back to impacts. So Andrew Moore and Grand Forks also developed an internal web-based tool that allows forecasters to conduct real-time sensitivity testing. So as I mentioned, a lot of times a 1 to 3 knot sort of increase in the wind speeds at certain temperatures and snowfall rates is all you need to tip the scales from a half mile or from a mile down to a half mile visibility. So forecasters can kind of sort of play around and do sensitivity testing as they're developing their conceptual model for what they anticipate going forward, and can also sort of determine, you know, how close are we to actually exceeding blizzard conditions? Does it only take a small increase in wind speed to tip the scales? And then you can sort of focus more in on those particular forecast elements. The standalone tool that I mentioned that we developed or in the process of developing does something similar. It allows you to get some sort of the sensitivity information in a gridded format within GFE. And here's just an example of one of them that's sort of one of my favorites, which is the blizzard wind threshold. So this will actually give you the example of what the sustained wind speed is that's needed to generate blizzard conditions that would give you the definite quarter-mile blowing snow in the NDFD weather grid at any given hour going forward through your forecast cycle. So maybe our forecast wind speeds are 25 knots or 30 knots, but we can see in this example that to get blizzard conditions, maybe we only need them just a touch higher in parts of central North Dakota. That's good, useful information, both for our internal decision making and probably for our external IDSS, where we can then relate to our partners that, you know, if the wind is just a little bit stronger, we do think we could tip towards greater blizzard style impacts. So how does the methodology verify? Well, it verifies pretty well. This is an example from Southwest North Dakota from 2018. What I want to draw your attention to is the background image is the Baggaley blowing snow model, or actually the actual Forecast Builder blowing snow methodology, accounting for the patchy as well, run on the observed grids, and so the observation grids. And so where we have areas of blowing snow that should correspond to a pot blowing snow of 40, the visibility in this case is generally 1/2 to 3/4 of a mile. But then we start getting down into the definite categories, the observed ASOS observations at that given hour, which are what are outlined in black there, really do fall down to 1/4 mile where we had blizzard conditions. It actually does match pretty well with those observations. Another case from Watertown, South Dakota, from this past winter, where Steve ran this, the visibility trends and time, again, verified really well with the blowing snow model output. There's a lot on this particular graphic, but what I want to draw your attention to is the wind speed, which is sort of in that green color, and the temperature. As the wind speed goes up and the temperature goes down, our visibility accordingly also drops. But the blowing snow probability, which is again color coded just like it would be in GFE, you see as it goes up, into the purples, and with blowing snow probability of a half mile goes close to 100%. That's when our observed visibilities, which is from the ASOS, which is in the blue background imaging there, really drop near to zero. It really does correlate very well, even over a time series of longer times. And it verifies well with visual trends and impacts as well. This is a case from western Minnesota, northwestern Minnesota. On the left, the blowing snow model output at that time, the half mile visibility probability was 40%. This would have corresponded to areas of blowing snow and the NDFD grids, the point and click, and you could see the snow plow cam there. On the right-hand side, the blowing snow model probability is it goes to 100%, and as we would have had definite blowing snow at that quarter-mile visibility tag in the point and click, you see the visibility drastically reduced, whiteout conditions on the plow cam. And so again, visually, it also verifies pretty well, even in the open country. And drifting snow impacts are also accounted for in this methodology. As we said, that was one of our goals with this, and it does. This is an example of a 24-hour forecast from North Dakota from 2018, where we had patchy blowing snow showing up across a good chunk of central North Dakota, and the yellow star there is unfortunately where there was a fatality that, as reported, was due to drifting snow producing patchy ice, directly a quote from the news reports. Unfortunate there was a fatality, but the potential for blowing snow in this particular case to produce impacts or the low drifting was actually identified and a message ahead of time because the forecast process allowed us to do so. So perhaps we actually were able to sort of prevent some other tragedy in this particular event. Certainly the tools did help us identify it going forward. So going forward, what's next? Well, it stands to reason that this methodology can certainly be applied certainly to individual model cores, but more importantly to blends such as the NBM. That's something that we're working on right now, and we're trying to figure out exactly what the best way will be to incorporate what we've done thus far into the NBM. One idea is to produce probabilities for each blend member individually and then creating final output rather than a composite approach. It's very similar to what's going to be done for the NBM p-types. Other discussions that we're having, and we are discussing this and working this with the NBM developers, it's on their radar screen. Hopefully version 4.0 might have some blowing snow items in it, but one item we might look at is actually producing a probability of blizzard conditions directly in the NBM, perhaps in addition to what we're using in Forecast Builder, what we need in our grids to sort of account for the spectrum of blowing snow. We've also got work ongoing to improve the methodology in several other areas, one of which is snow crusting, where short duration, like 1 to 3 hour warm-ups occur. So that no-risk background data that we're using right now and then applying it with temperatures, anytime the temperature meets or exceeds 35 degrees, that snow is essentially assumed to be crusted over. But we know sometimes if we only reach 35 degrees for 1 hour, that might not be the case where it's truly crusted over. So we're doing some work with that. We also have a scenario that happens in our part of the world in particular, and certainly in mountainous areas and elsewhere, where if we have long durations of snowpack staying below 35 degrees, 8+ days, it's actually still uncrusted. But the current methodology, because we're only saving 7 days worth of no-risk grids in GFE, sort of makes it fall back out of that state. So that's something, again, on our minds that we're trying to identify and work through in our coding. We have some ideas for that already. And then accounting for some of these cases where a snow crust maybe can break. There's some research out there that suggests even after the crust is broke, if you get a high enough wind, it might break in certain cases. And then do we attempt to account for the transport of blowing snow from upstream? How far does snow actually be transported and blown? And which there's probably some other research efforts out there that are working on that. And then finally, what we really need as well is a larger scale verification effort. I showed you some examples of how this really does verify well, but we really want to get into a peer-reviewed verification effort against observations and really in varying climatological and topographic regimes. One of the big questions that comes up with this is how does it verify, for instance, in the treat areas of northern Minnesota? Does it verify well? It probably does in the open areas, but what are we trying to account for? And do we actually need to apply this model over edit areas that are maybe more prone to blowing snow? We don't know, but that's some of the things that we're looking at, and that would sort of fall out in part of that larger scale verification effort that we're in the early stages of thinking about and plan to work on over the next year. So with that, I thank you for your time, unless anyone has any questions.